Hello, my name is Nigelargriffiths. I work at IBM Power Systems Europe on AX and Linux. This is yet another one of my little projects looking at performance monitoring on our Power-based machines. If you want to get in contact, you can see my Hotmail address at the bottom, and also the files and details of this project are at this tinyurl.com nextract+. It's one of the AirExpert blog articles. It's actually only a Python library and a Python program, which are very small, easy to install if you have Python available. In this video, we're going to look at nextract+, which is very powerful in the amount of data it can present to you and very quick to install. In this video, we'll be looking at the dashboards and graphs. If I used to Power, then the bottom half of this diagram is very obvious to you. The Power machines are connected to a HMC, a hardware management console, and from there we can start and stop our virtual machines and our physical machines as well. The HMC provides a REST API for the performance data, and nextract+ is a Python program that pulls on that REST API to get all the data available on your HMC or HMCs if you've got lots of them because you have lots of servers. That data then is pushed into a time series database called InfluxDB. We then can go to the program called Grafana, log into it. It will connect to the InfluxDB to get all the time series data that you've been saving over a long period, and then it will do the graphing for you inside a web browser. Now, just to go a little bit further in, the HMC is actually connected to the service processor in the base of each of the machines, and from there it can actually extract data from the hypervisor. So it understands about the virtual machines in terms of the CPU cycles that it's using, how much memory it's got, and that sort of thing. The way we virtualize our I/O is we have the VIOS server, and so the HMC talks to the VIOS server when it's trying to set up things like virtual disks and virtual networks. So this is where the data is coming from. The HMC, although it has some instances of talking to the operating systems when it's doing particular things, like even in the mornings before it changes the size of the virtual machine, it's not really on a day-to-day basis talking to the operating systems. So we have details, the graphs about the whole server, shared storage pools that I've been using quite a lot. We have the shared processor pools. This is typically used for license management. Then we have the virtual I/O server, those virtual resources like virtual networks and virtual storage, and some of the details about the logical partitions themselves. There is some data that you won't get out this way. So if you want the details of your operating system, like the processes, the run queues, all your different disks and what they're connected to and how they're being used, or the networking, if a operating system has an adapter in it for storage or network, and it's directly connected to those sorts of devices, then none of that will come out through the HMC. I, of course, write the njmon and nmon tools, and they can be used to extract the data from AX and Linux and pushed it into InfluxDB as well. One thing that we haven't got is the information from the IBM I. They have their own special tools. Everybody says iDoctor is particularly good at that. But the nextract can pull a lot of the details about IBM I because it's operating system agnostic. So here we go. This is the nextract+ dashboard. There's actually around 50 graphs in here now, so I could have whizzed through all these and you just said, well, that's a lot of graphs. But I thought I'd go through them blow by blow, let you have a little look at them, and I'll explain some of the details of how Grafana actually is working, how things are put together. Right then, up on the top right in here, this is how we select the time range that we actually want to look at. We're looking through this particular time range in here because the stats look pretty nice, but we could immediately go for a look at 1 day or 1 week. If we scroll down in here, there are a month, a quarter, a year's worth of data if we have that actually in the database. As we're doing rapid prototyping, I've only got a couple of weeks worth of data in there at the moment. Over in here we have what are called Grafana variables. So this is a pop-down list of all the servers that we have data for. So it's looked through the data and found the server names in the data, and then we can select which one we want. We're looking at the moment red. Then for this variable, it will look through all the VIO server names and then select again on the server name. So these are the two VIO servers, and we just use the VIO server name red and red in here so we can see they're the right two VIOS servers. Then we want to pick up the LPARs. Again, these are the LPARs that are on this particular server. It's very common for you to have two VIOS servers, so these will actually be connected to both of those VIOS servers. In here we have a reminder of which this is actually looking through the database and saying, hang on, at the moment the data you're looking at came from nextract plus. This is the REST API. If you have older HMCs, it might have 1.1 or 1.2 in here, in which case some of the stats will just be missing or different or wrong even. So here's the date, the time rather, and this is the order in which the dashboards appear below, and I put some release notes in here. Right, now the first thing is we're going to have in here the statistics across all the servers, so we can look at everything, and then we can ask it to pull out how busy each of the servers are at the server level in here. So in this case, in a small computer center in South Bank, London, UK, and we're not running production workloads. This is used for developing things and prototypes and demos for customers and that sort of thing, and actually creating videos. So in here we can actually look at this one here. If we put it at the top in here, it says Yorkshire is using 9 CPUs. That's the busiest one in this particular period. We have run some sort of small benchmarks of things where we can actually knacker a machine and everything goes very busy. But you can see in here all the various ones going up and down over the time period we have in here. 8:50 in the morning to 10:40 in the middle of the morning. Now you might say, well, that's interesting, that's the busiest server we've got. I'm looking for some spare capacity. So we got down here what's available. So if we hover over this one, again, it's Yorkshire. Now Yorkshire is our biggest machine. It's an E880 with 64 CPUs. So you'd expect to be the one that's going the fastest and has spare capacity on here. So that's got 24 CPUs that we could use it. If you're looking for 20, then it will just pop onto there with no problem. Those CPUs are currently in the shared processor pool for any LPAR or virtual machine that is going, if it's uncapped, it actually wants to use more CPU power. On the memory side, well, and again, guess in here we can see Yorkshire is the one with the most assigned memory in gigabytes. It's assigned to our LPARs of 600 gigabytes. If we pop down in here looking for free space, we can say Yorkshire, well, it's got 1.4 terabytes. I guess we've got 2 terabytes of memory on that particular machine. So we can see what's being allocated the most, and using the CPU, and where there's space capacity available for adding new workloads or making a virtual machine bigger. So we slide down in here. This is the statistics for a particular server called Red. It's one of my favorites. We see it's Power9 S924. And so we've got the CPU over here. We can see it's the configurable is 16 CPUs. That's how much it's got in there. We're not using capacity up random mine or anything. We hover on here. It's peaking at, it's over here actually, it's somewhere over here perhaps. It's peaking at 8 CPUs are busy. And we could allocate another 4 CPUs, 4.15 CPUs to the current logical partitions, or adding new logical partitions. Over in here is a physical view of the CPUs. This is like the entitlement view, if you like, and this is the virtual processor view of the CPUs. And so we can look at both of those here. In memory terms, we have 256 gigabytes available, and we've in the machine available, we could assign to virtual machines another 100 gigabytes of data. This is another way of looking at the same data. Sometimes it's nice to see the proportions a bit better. This is being used by VMs, this could be used by VMs, and this is persistent data, memory. That's used by SAP HANA, for example. Okay, down in here we have a little note of the machine type and serial number. This here is the MTM machine type model, and that's obviously a Power9 machine called an S924. You see the 2 and the 4 around the wrong way. This is IBM gobbledygook for the actual product name, and here's the serial number. Some things in here that I've never seen before, right? Fascinating and instructive. This is the system firmware, which is called the hypervisor to everybody else. and it's been using CPU. And you see, so there's a big spike, and it's every hour and a half, 90 minutes, there's a spike in here, and you think, wow, what's it doing? But if you actually look over here, it's using 5/100ths of a CPU for a small fraction of time. So there's some sort of daemon going around, ticking around, doing some housekeeping or something like that. More important over here is the hypervisor actually uses memory. It uses memory because it's managing the data structures that give you the virtual memory inside your logical partitions or virtual machines. And also, if the hypervisor is managing some of your high-speed network adapters, for example, then it'll allocate buffering space, otherwise you can't get up to your full line speed. You have to buffer things because it's coming in so fast before you hand the data over to your virtual machines. So it's currently using 118 megabytes of data out of our 256 gigabytes. Now down in here we've got shared processor pool information, and this is quite interesting and quite important because it's a licensing thing. Now in the movie I'm not going to show you the transitions. I'm going to flip to a different machine that has a more interesting data in here, so I'm going to pop over to Ruby. That's because rather than just the default, it actually has a pool. Wow, what an original name, my pool. Typically these might be for managing particular applications, perhaps a relational database like DB2 or Oracle. You're paying a per CPU core license, and so you can put all the LPARs using that software into one shared processor pool and monitor how much you should be paying to your vendor. So here in the pool you can see it's using 2.5 CPUs, and it died off a bit to 1.5 CPUs. In the this is the shared processor pool, how much is available in here. Over in here, on this machine it has 32 cores, so available with the default is 32, and there's been 10 allocated to my pool. But if I'm only using 2.5 CPUs, I could take this number down to say 3 and then stop paying quite so much to my application vendor, for example. But a lot of people want to measure that, and there it just falls out of the woodwork if you're starting to use these stats this way. Right, next down in here we've got the VIOS server data. There's got a lot of this because, as I said, the HMC is talking to the VIOS server. I'll pop back again to red and select a slightly busier logical partition down in here. So I'll come back down in here. So here's red VIOS server 1. We can see in here the current VP, the virtual process count, is 2, but the entitlement is 1. So if you're uncapped, it can go up above that, and you can see the actual VIOS server is not doing very much at all. While we don't run big workloads on our machines, well, we can fake them, but we don't just like hammering the machine all day long using lots of electricity. Over in here we have the memory. So it's been assigned just under 8 gigabytes. That's probably 8 gigabytes, but then there's some housekeeping memory goes missing. And then we're actually using only 4 gigabytes of that in this case. So that's good on the VIOS servers. It's got some spare capacity, it's got plenty of CPU capacity, and it could double in size to 8 gigabytes of memory if you wanted to. Now we're drilling in. This is the VIOS server networking stats. Of course, VIOS servers tend to run shared Ethernet adapters, and this is just saying there's 8 LPARs attached to your virtual networks in here. If it says over here, if this says no data, then there's probably some errors when we're collecting the data, and so we don't get this particular number. You need to go and look at the daemon collecting the data, the nextract plus program. This is an iceberg diagram, so we have reads coming in above and writes out to the network below. You can see that they're fairly even matched. Yeah, it's a regular pushing of data across the network. Down in here we have the packets per second. It looks like the blocks are the same size all the time, so they look very similar. Over here we have the virtual network. Of course, there's chit-chat going across the shared Ethernet adapter. So we have and we have some more data going out in here. So we're sending. You can actually see in the keys in here, the big long thing is the name of the adapter inside the machine. And we can see that it's VLAN 62 in that particular case here. Then we've got shared packets going across the VIOS server. Again, 2 different sorts of data in here. Here we have the shared drop packets. I'm going to have to investigate what's going on here. This is a lot more than I thought. There's some packets being dropped on our real network over here, on our virtual network. Well, that's all in software, isn't it? So we don't expect problems in that unless we got bugs. So that's working okay. So I'll have to look at ENT5. Maybe we got a flaky cable in there or something like that. And here's some details more about the SC, the actual adapter that is sitting on. So you can go and find that easily enough inside the machine, and the virtual adapter in here as well. Now we're moving it over to storage. We tend to use shared storage pools, and every LPAR is using that. And we can see there's 8 attached to that again. And in here the shared, so this is the fiber channel. The shared storage pool is running a set of LUNs out to our V7000 disks. And you can see, because we're not doing much real I/O for applications, we can see that the fiber channels was used to push some data out on a regular basis. Then over here is the ops per second. The graph shapes are very similar. Down in here we have the physical network stats for the VIOS server, looking like this, and the operations per second over in here. And we don't have any LUNs that are mounted on the VIOS server and then shared with the virtual machines as a shared disk. So we don't have any of this sort of storage traffic. Here's the actual shared storage pool. This is nice to see. Pretty hard to do it otherwise. You can see in here the SSP is called Orbit, and this is the data being read and written, and the operations per second. Now this is telling us how much space we've got in our shared storage pool. So we have 6 terabytes in size, and we're only allocated half of that, so we've got plenty of space. We can over allocate it because of thin provisioning. Now if we go down to here, this is the graphs for all the LPARs on this particular server. So this is a little bit like the one we did right at the start, but now we're looking at the LPARs inside a server instead of the servers inside our computer room. You can quickly see up in here, Silver 2 is using nearly 3 CPUs during this time, and Silver 2 is running by, this is the name of the LPAR as seen on the HMC. Now that we use Silver 2, that's actually the host name, and then we actually note which operating system. This is actually one that's running the InfluxDB and Grafana, and this is probably getting busy because I'm running lots of copies of the nextract program at the same time over that half an hour or so. Okay, so, and again we can see the ones that aren't so busy and the ones that are busy in here. Oh, you notice in here it says unstacked, so the top one is the busiest one. Sometimes you want to know what the overall thing of the CPUs are, so this is the same data stacked. So you can see the big one in the green at the bottom in here. But on our server, which had 16 CPUs, if I got that right, we're peaking up here to 8 CPUs actually in use for all the busy logical partitions in here. There's some in here. There are Silver 7 is using 3/100ths of a CPU. That's just the timer interrupts kicking in. Then we got the memory assigned to each LPAR, and again we can look at the top one. That's VM192, has 16 gigabytes. Oh, there's another one actually. Silver 6 has got 16. It's underneath the other one, but you can't actually see the 2 lines on the graph. Here's another way of looking at it. You can see this is the big one here, Silver 6. Here's the other one, VM192. So we can pick those out very easily. There's a whole bunch of the same size in here, isn't it? This is 8%, 8%. Yeah, so that's 8 gig. Over here we have the VP to E ratios. This is the virtual processor to entitlement ratio, and we would like to keep it around about 1.5. So you're keeping your logical partition down to sort of a minimum set of CPUs because that's efficient. The caches warm up on them. We can see one particular LPAR or virtual machine 194 has a VP to E ratio of 20. So maybe it's got one CPU allocated, but 20 CPUs, virtual CPUs, won't actually fit on this machine. That's running inefficiently. It's using 5% of lots and lots of CPUs. Not a good idea. Now, if you have very, very peaky workloads, then perhaps you could justify that. Normally, that's regarded as a mistake, or somebody didn't know what they were doing. Some of the stats are down in here in a table. That might help if you've got 200 LPARs on a particular machine. Then you can order them by particular numbers and see which one's got the biggest entitlement and the biggest VP, for example. These we've seen the numbers we derived off that. This is the actual VP and entitlement here, so you can double check that everything looks about the same if that's what you're aiming at. Okay, down in here we have two sets of utilization numbers for capped and uncapped. I don't understand really why there's two sets of those numbers and why they look so different. That's something I need to study up and look at. But we have those two views of the data. They're in the stats provided by the HMC, so I'm just graphing them. We'll have to work out exactly what those things mean. Have to check the documentation if you can find any. Then we have the virtual networks. So which of our servers, we've got read and received and send in here, and we can say this is the guy Silver 2, which is our InfluxDB is getting most of the data. Well, that's the data being sent to the InfluxDB, so we can immediately see it there. The data going out is a lot less. Then we have the virtual storage, bytes per second in here, and operations by second for this particular logical partition or VM. This is a little bit of an odd one in here. When you allocate CPU time to a logical partition, it finishes all its workload, it doesn't immediately give the processor back to the hypervisor for somebody else to use, because you're hoping that some interrupt timer or network or storage device will interrupt and give us some more work to do. So you hang around for a little bit. This is the actual time that is actually in here. This is straight out of a hypervisor that's aware of this. Your operating system isn't really aware of this. But there we go. We can see up in here, Silver 2 is hogging the CPU quite a lot of the time, waiting for more interrupts. Probably means there's a very peaky workload, so that makes sense. Particularly as we're not running out of CPU time on this machine. It's only half busy, so if it thinks this LPAR's got something to do coming up soon, then it might as well stay there and hopefully pick up the interrupts and carry on. These next two graphs are highly experimental. The first one is the time per instruction execution. I think this needs some special tool switched on inside the actual processor to get that count. And the one on the right is the time spent waiting for dispatch. This is a hypervisor number that we don't normally see, but it's the time the hypervisor might have to wait before it can get your LPAR running on a CPU core due to other activities. These are tiny, tiny fractions of a second. Now we're going down to the graphs of a single LPAR. So we selected Silver 5, so these are a bit simpler in here, looking at a particular virtual machine or LPAR. We can see it's running AIX. I did notice it above for the VIOS servers as well. We have this Affinity Score of 100. This means all the CPUs that have been allocated are on the same, this is Power9 processor, as the memory that's been assigned to a logical partition. So that's good. It's high affinity. So CPU over here, the logical memory that's been assigned to it. We're not sure from the HMC what operating system is doing with the memory. All we can say is it was allocated 8 GB and it's doing something in it. The VIOS server gave us a little bit more details about how much was used or on the free list, but for our regular virtual machines we don't have that. Then we have networks over here and the packets, and a squeeze in the middle here. No packets are being dropped, that's good. Then we have the different sorts of storage in here, just seen as generic virtual storage. The vast bulk of the storage is supported by the VIOS server as virtual SCSI. LPAR doesn't know what's actually backing it up. So this is why it comes in as generic storage bytes, and it's not very much, is in here. 7.5 kilobytes a second going out in little peaks. In here, we've tried to select the top 5 servers. We've had to name them in this graph, so this won't work well on somebody else's machine, but you can probably know which are the core machines that you want to monitor. Make sure that they're okay. They're the ones running the business, and the important ones for sales, perhaps. And so we got hard-coded in. This is stacked over here, and this isn't stacked. The same sort of thing with memory to work out the machines that have got the most memory in here as well. So here we have the fiber channel storage, SRIOV, and this is old technology, the HEA. I think this is only available actually on Power 7. Going to quickly move to a machine that has some virtual fiber channels, so we can see some graphs. Okay, here's some data from a machine from the lab services guys. Stu Conliffe has given me access to them. We can see here's the virtual fiber channel. It's only doing write at the moment, bytes per second, and ops per second over here. And we can see here that it's all running at 8 gigabits per second over those connections. Right, well that's it for now. If you have SRIOV data, then they should appear in here. Well, that's quite enough graphs for now. As you can see, there's graphs at various levels in the computer room that we can get from the HMC. And that's not bad for something like 600 lines of Python code. We could try and reduce that a bit, but it's fairly simple to actually operate and do it. I will be creating some more videos in this series on how the stats are actually collected and show you that working. It is quite simple to actually operate. And then we'll look at the details of installing and setting up. The installing of nextract is very quick, 2 files. The HMC, you need to switch on some features, and then you have the InfluxDB and Grafana, and actually using the dashboard. So that takes a little bit longer to set up. If you've already got njmon installed, then that's already done. So the extra bit for nextract plus is very small. Don't forget, once you've got a time series database, you will never want to go back. If you're still watching, well, thanks for sticking with me. Don't forget to give us a thumbs up. Always gives us an excuse for some more videos. Thanks for watching.